That's great. Thank you very much. Yes, so I am currently an assistant professor of environmental sciences at the University of Birmingham. I've previously worked in several different institutions, as many of us, and I'm going to present some of the work that I have done largely at InSAR in Grenoble in France in collaboration with CNES, which is a French space agency, but also in my contextualization, you will see it's done with collaborators at ETH in Zurich. So my presentation is going to focus on results that we synthetic aperture radar differential interferometry, and specifically on landslides identification, but landslides precursors. And I will the second half of the presentation on the case study of a landslide in Peru. So I just want to give a little bit of context that are not overly familiar with InSAR. I have a feel for what we can actually do and landslides. And it's not meant to be autoreferential, but I will use largely my work to give you this context. So currently try to identify previously unknown landslides over large areas. And we can do that in a very simple way by using single interferometry, which are just a snapshot of the deformation between two SAR acquisitions. And this is just an example. As I show here, we have the interferometric signal, which is the wrapped phase, that can show some patterns that correspond to activity features. For example, in this case, on a deep-seated landslide in Bhutan. And this can be very useful. We've seen in previous presentations how discovering the distributions over a large area can be very important. It can give inventories to work with, evaluate predisposing factors over large regions, and we can have a first assessment for land use management. And so here of a map that I have compiled with my colleagues for Bhutan, which was a region for which very little was known in terms of landslide area. Only a few cases had been studied previously in this region. And this shows how we can combine different sensors and a large number of produce essentially what I've called a likelihood of activity map, which can be used as a hazard index map. So it shows in relative terms where we have more likelihood of activity on slopes. But the quantification of is actually something that has become increasingly popular, and this is done by generating time series using multi-temporal approaches. Briefly some examples this afternoon, and they are very useful, of course, because we can get absolute measures, the displacement and the displacement rates. And so we can also hope to identify the actual processes occurring on slopes, even attempt to be a bit more specific about the hazard level of specific sites for example, site suitability. And this is an example of a map that I've produced for the same area that you've seen before using time series, the velocity maps and the cumulative displacement maps. And you can see that there is a lot of information here, but if we compare it with the previous map, we can see that although some of these polygons are in similar areas, there isn't a perfect overlap. Hopefully you can see that. The two different methods that are based on InSAR give different type of information, and they should be looked together as opposed to taken as interchangeable, because they aren't. We can, as I said, we can have a look at potentially site, and even when we process at the large scale, there is some potential in there. And this is just one example of a particular slope that I have identified in this large area in Bhutan, where I did an entire frame processing. And for sure, we can see some slope. They are at most a couple, like 200 millimeters per year. In fact, this is displacement rates. So, sorry, yes. So basically, we can definitely identify some trends, but we have some verification, some validation on the ground, if they look realistic and they're real, or if they look realistic, but they are, for example, underestimated. So here I have a slide just to suggest that there might be a potential pitfall here. So it is great what we can do about what we're looking at. We know that landslides undergo transitions. They can creep really slowly periods of time and then suddenly transition into faster, into accelerations. But also at some point, they can even be governed by different mechanisms and responding to different forcing factors. And they start to respond with phases of acceleration and decelerations, which can happen over a relatively short period of time. And we captured these with InSAR. This is the question. When I see time series from InSAR, I always ask myself whether we are looking at displacement rates or something that looks real, but maybe is underestimated. I got inspiration a few years ago from this article from Intreria and his colleagues, and they have shown for this particular landslide in China, which you can picture on the left corner, that they actually were able to retrieve a very nice acceleration signal over the course. And that they've also said that by plotting the inverse of the velocity in this particular case, they were able to retrospectively potentially predict with quite good accuracy the time of failure for this landslide, which would be fantastic if we could do that. But the reality is that the retrieval of reliable time series, so not only realistic looking, but reliable, actually be hindered and is often hindered by low coherence, which is basically an instability of the phase signal, which is given to land cover changes given by vegetation or snow, or even a veneer of loose material on slopes that moves like not as a coherent body, let's say, with the rest of with the landslide body. And also because all these phases of accelerations and decelerations, this is also something that complicates the retrieval of this time series. And I just want to show you what I mean. So we have here on the top left a snapshot of the European Ground Motion Service, which basically is an excellent product where InSAR is updated, I think, every 6 months from 2016. So this is incredible what they have. But when we zoom in, so of course, a lot of important information is contained here. But when we zoom in into the two little squares here in France, these are just two. There are many more. We can see that we have very little points, and the few points we have are green, which would suggest that no displacement over these slopes in that period of time. So 2016 to recent, I don't remember when I took this, not very long ago. But actually, there are two landslides that moved, that underwent significant accelerations, so we can't see them with the most classic processing approaches for time series generation. It moved by several meters. Here we have June 2016, July 2016, so well included in these steps. And here we have another landslide, which we can see moved by several meters again in the same observation window. Were observed with different methods, so optical image correlation and ground-based InSAR. So we really have to be careful about that. And now we example, which is the Achoma landslide, which is a landslide in Peru that failed catastrophically in 2020, 4 years ago, and it was completely unforeseen. So the reports we got is that locals only started to notice sign of the deformation before the failure occurred. So when there was no time to really do anything meaningful about it. And this landslide was very big, well, is very big. It blocked the river, and it's estimated to be about 20 million cubic meters. So it's, and when we look at another platform that this time is based on work of some of my colleagues in France, this again shows the map based on another approach that is quite common, the ESPAS approach. And again, we can see a big red block, which is deformation associated with a volcano in the area. But when we zoom in into this square, the white square, hopefully you can see, we can see we have some faint black polygons that are the landslides in this area. And this is our landslide, the Achoma landslide. The InSAR signal, again, We don't see anything. Yet we are well within the window here. So this data is from 2022 and the landslide fell in 2020, but we cannot capture it. So if I show you of the wrapped interferogram, so this raw interferometric signal for this landslide, this is what we see. So even InSAR, hopefully you can see with your eyes that we have some patterns in the center of this square, which are squares, which are centered over the landslide. You can see it here, and you can see it very well here, but also, hopefully you can see how noisy interferograms are. Therefore, in the absence of a smooth gradient, the retrieval of time series is really difficult. What can we look at instead? So this is a marker and potentially a precursor in space obtained with the coherence. The interferometric coherence, as I mentioned before, is a measure of the phase stability in space, in a window of pixels. And in line with the rainfall, you can see the wet seasons. And we can see when I show you these squares with coherence maps, show some very interesting rope-like features that appear to mark what will become the band slide. And the interesting thing is that already from 2015, even if I don't show it on this slide, we see it at in time. So that means that this particular part of the signal can, at least in some cases for certain types, can already identify gravitational features well below they are visible on the ground. And when we mean parameter, the coherence in time, here I show the mean, the average coherence within the landslide polygon, which is the area with a yellow line on this graph, and the average coherence in the surrounding area with the green line. We can see that it goes up and down, following a certain seasonality, and it goes down when during the wet season, as we can. And if we look at the very end of this temporal window, in a few months before failure by the red line, we can see that there is a big departure of these two curves. When we compute their ratio, landslide, over the coherence in the surrounding area, we see that from April to June, we have a drop in this ratio. So at this stage, I don't know yet how this can be used in a predictive way. We have a precursor that deserves to be investigated further. And this map shows so the image, the data, the cumulative displacements obtained with optical image correlation that was processed by my colleague at ISTER. And we selected a point here where you can see right in the middle of the landslide, more or less, where the displacements were really large. We compared the displacement obtained with the optical image correlation that you can see here in green with my ratio. And we can see that there is a very good correspondence in time when these two signals begin to appear and begin to be clear. And then we did another thing, so I will not go into the details of how of the method, but we devised a very a simple method in a conceptual sense to try to extract a dimensionless activity quantity directly from the wrapped phase. So without going into all the processing steps that are required for the classic time series generation. Every point on this graph is an interferogram that was available to us. And the color is difference in the length. So the interval between one and the first and the second acquisition. And we tracked a measure that is a relative measure, as I say, is a dimensionless quantity, in fact. So when this quantity is 0, it means that we don't see any displacement within that. And then above 0, we see some displacements. And here we can see a few interesting things. First, you can see a bunch of interferograms here that are gray. So at this point, the displacement were being too fast. The noise is really too high. No method can allow us to really extract this dimensionless quantity. But we can see that very clear acceleration phases a couple of years before, like within the 2 years prior to failure. And this is also quite nice. They appear to correspond to the onset of the rainfall, which are the blue curves. So every blue curve is one hydrological, so it's one wet season, basically. And we can see that there seems to be a correspondence there, but in the season, in the dry season between 2018 and 2019, despite the rain stopped, there appeared a continuation of the activity of the landslide. Then the landslide quietened down again in 2019 into 2020 to resume again in 2020. And interestingly, the runaway acceleration was not in a period characterized by higher. So this seems to point to some sort of progressive failure. So there is a certain control of the rainfall, but there is something going within the landslide itself that is explaining the displacements. We can also see that we have, towards the beginning of our test, we have 5 interferograms that appear to show some displacement that occurred over a very short period of time, and then the landslide stopped. When we look at, for example, seismic activity, so the green bars, on this graph represent the peak ground acceleration earthquakes in the proximity of the landslide, we can see that probably some of these events, these displacement events, were triggered by higher PGAs. In fact, we don't see as high PGAs later towards the first part of the period. Here you can see potentially, I told you I extracted a dimensionless activity quantity, but then here we have cumulative displacement in millimeters. So I basically just use ways to estimate what could be the displacement. This is not really accurate, but it gives a sense of what the displacement on the basis of the gradients that I was observing in the InSAR signal, but I don't have time to go into this detail now. But it's just an estimate, so it's not meant to be a accurate measurement. But yeah, so what I think we're seeing is probably a period in which it's really undergoing these transitions, this fast transition between accelerations and decelerations. And when we plot the inverse velocity of these three, for example, we can see this asymptotic decay, which would really exactly show that we are probably in this sort of phase if we're looking at the creep history of the landslide. So this is very interesting because basically we are revealing all of this in the absence of a classic series generation. The last thing I would like to show you is the complementarity that there is between the optical image correlation, which is in blue, where we can't really say a lot in the period between 2018 to 2020, but the last acceleration is picked up really well. And InSAR, which is the method that I have devised with this study, where we can actually see accelerations in the years prior to failure. So this would give a very long period of time to start to investigate better what would be on this landslide. So just to conclude, we are now, I feel like I have still this question whether we need specific tools for landslides when we're using InSAR, as opposed to relying on the most classic approaches. Monitor more reliably landslides from space. So I just conclude leaving you some of the key messages with the methods that I've shown you. Well, or that I haven't shown you, but I've shown you the results of those. We can, as a precursor, up to 5 years before failure in this particular case. And I haven't shown this, but I can tell you that this was not an within the valley in which this landslide is located. And also we can show that despite the noise, which would have hindered the generation of a classic time series, the rapid phase signal, which is really the raw interferometric signal, can still retrieve some sort of accelerations, indicating progressive failure, probably, and also showing the beginning of a critical phase of instability already 2 years before failure, with a good lead time to investigate this landslide better. So I also shown that InSAR, so this particular method, which is based on part of the InSAR signal, is complementary in series. So again, not interchangeable, and also to optical image correlation, and so that no method, I think, can be reliably used for all landslides in isolation, especially in the absence of validation. And so that there is benefit in attempting to develop potentially to use other indicators such as interferometric coherence or the rapt phase when we can't reliably return series of displacements. So I conclude here. Hopefully I didn't take more time.